profesor O'Rourke es uno de los, ¿sí se oye? Es uno de los ingenieros estructurales e investigadores más sobresalientes del mundo. Profesor de Ingeniería de la Cátedra Tomás R. Briggs en la Escuela de Ingeniería Civil y Ambiental de la Universidad de Cornell desde 1981 y profesor visitante en el Reino Unido y Nueva Zelanda con presentaciones técnicas en varios países, destacando México, Estados Unidos, China, Japón, Nueva Zelanda e Italia. Thomas O'Rourke se formó como ingeniero civil en la Universidad de Cornell y es egresado de la maestría en ciencias y del doctorado de la Universidad de Illinois en Urbana-Champaign. Su línea de investigación ha sido el comportamiento de las líneas vitales ante sismos. Es un líder reconocido mundialmente en el desarrollo de enfoques novedosos para diseño detallado y construcción de estructuras de concreto y acero. Ha desarrollado novedosos enfoques de análisis de la respuesta de los sistemas extendidos ante sismos. Sus trabajos se han traducido en requisitos, en normas y reglamentos de construcción. Su prestigio lo ha llevado a ser electo presidente del Earthquake Engineering Research Institute, a recibir la medalla George W. Hausner, considerada como el reconocimiento de mayor prestigio en los Estados Unidos a las contribuciones en ingeniería sísmica, a ser nombrado miembro de la Academia de Ingeniería de los Estados Unidos, así como a recibir varios premios por sus artículos en revistas arbitradas y sus conferencias. Con ustedes el profesor O'Rourke. Thank you.
Thank you very much. And again, I'd like to express my gratitude to the organizers of this symposium, and in particular to the College of Civil Engineers of Mexico for putting this symposium together. It's perhaps a profound irony that our borders that divide us are the borders that unite us. And my talk today is going to focus on issues that transcend and cross borders. Natural hazards, which have been in the news and affected both countries to a profound extent recently, and need to be addressed in terms of the context of designing, building border crossings, developing and uniting our countries with respect to a common border, with common infrastructure and common facilities that support and benefit the communities of both nations. I'm going to talk, in doing this, about critical infrastructure. And the critical infrastructure in particular that I'll concentrate on will be water. Water, of course, is emblematic. The Rio Grande causes or creates a border between the United States and Mexico, and it's emblematic of the importance of water in our critical infrastructure. And perhaps by learning how other communities have dealt with natural hazards, particularly earthquakes, we can learn something about how we can improve the border, and beyond that, our infrastructure that we all depend upon. Our modern communities, in fact, are conjoined with infrastructure. The infrastructure helps define the community, and of course, the community helps to define the infrastructure. This is a picture of the corner of Wall Street and William Street by the New York Stock Exchange in 1920. And it's representative of the type of infrastructure that we will find beneath the streets of our cities in Mexico City, in New York City, San Francisco, and elsewhere. It is, in fact, our national treasure. It is the complex of resources and facilities and services that unite modern communities. These are our lifelines, and like every treasure, we bury it and forget about it. And it goes through transformations that we don't understand. And of course, because of proximity and also interoperability, it is tremendously conjoined in the sense that if one of those pipelines were to break, the damage would cascade into the telecommunication system, the electric power system, and so forth. So these are the facilities that we'll be talking about in this talk, and the topics I'm going to pick are hurricanes and earthquakes, infrastructure characteristics. I'm going to tell a story about San Francisco, and then I'm going to tell a story about Los Angeles, and then I'm going to say some completing words with respect to hazard-resilient infrastructure. So let's start with hurricanes and earthquakes. When we look at the United States and Mexico and its border, we have earthquakes that not only cross the border, but are on both sides of the border and have helped to define some of the challenges that both our communities, both our countries face in the recent past. Similarly, we have hurricanes that affect both countries, both at the border and across the border, that we need to have some common cause and some common way to approach these things and work together to make our systems more resilient and to make our engineering and planning and communities work better. In fact, we can take one particular fault, the imperial fault, and if we look at the border between the United States and Mexico, the imperial fault crosses that border as a kind of an emblem of common cause here. There was a 1979 Imperial Valley earthquake which caused damage on both sides of that border. We go back to 1940 to the El Centro earthquake. That was another one that caused damage on both sides of the border. And in fact, if we trace back year after year, there are a number of earthquakes just on that one fault. We've had some terrible recent earthquakes in Mexico, and certainly those of us in the United States who also have to deal with earthquakes send our condolences and our affirmation to work with you to make our communities better in the face of earthquakes in the future. In fact, one of the missions that I'm on during this particular visit is to help coordinate a U.S. and Mexico joint evaluation and inspection and understanding of the effects of the two recent earthquakes, the September 7th earthquake near Chiapas and the 7.1 magnitude earthquake of September 19th. Also, hurricanes have a profound effect on both the United States and on Mexico. Most recently, our problems have not been earthquake related, but through the recent hurricanes, Irma, Maria, Harvey, we've had terrible destruction, loss of life, and problems there. And it harkens me back to the 2005 hurricane season when we had so many named storms that we ran out of the alphabet and had to go to the Greek alphabet to name them. I call that the Greek bailout of our alphabetic system. And some of the more serious earthquakes of that time were Katrina, Rita, which had a profound influence, of course, both of those on New Orleans, the first one being the major effect, but also in Mexico, Hurricane Emily. And I'll tell you a personal story. We were going to take a vacation at a place near Playa del Carmen called Expuja. And Expuja was destroyed by Hurricane Emily at the beginning of that hurricane season. And then we decided to take a vacation at Cozumel. And then that was destroyed by Hurricane Wilma at the end of that hurricane season. And there's a tremendous story in the restoration of Cancun and the whole Maya Riviera, which was very effective after Hurricane Wilma. And I've always wanted some common dialogue between our Mexican friends and colleagues and the United States friends and colleagues about how both those hurricanes were treated and attended to. Katrina in the United States and Wilma in Mexico, because both of them had profound influences, and of course they were terribly destructive. In fact, Hurricane Katrina, we typically talk about an evolution in policy. This created a revolution in policy, where we went after 9/11 from a code or an approach that was adopted by the then Department of Homeland Security for the protection of critical infrastructure to the creation of resilient communities. And we're still exploring that transition today. So let's talk, before we tell some stories about communities that have had to deal with natural hazards, particularly earthquakes, because that's very topical and important for borders. Let's talk about some very important characteristics of infrastructure. we like to look at infrastructure as being geographically distributed. That is, where do we get the resources and the services that support all the buildings and support all of the activities that we have in our communities? And we get them from geographically distributed systems such as electric power, gas and liquid fuels, telecommunications, transportation, wastewater, water supply, and flood control and levees. And we understand that these systems are interdependent, so that the solution here is a collective solution. We should not look at one of these systems out of context and individually, but we should look at them in a united way and come together to understand how they influence each other and how they can best be managed as a whole. We also know that they're interoperational in cities. They are very closely located and in many cases unknown in terms of those locations. And they are also interoperational. So if you lose electric power, you lose the ability to pump water. And if you lose the ability to pump water, you lose the ability to provide water for communities. You lose the ability to provide water for fire protection, and then you lose buildings. And this goes on and on with respect to transportation and power and water, and it even affects our financial markets. Perhaps the most important interdependencies that exist in infrastructure, and if we look at these infrastructure systems that I just identified as being shown on this screen, not necessarily connected with each other, but on the same screen, a good analogy for how they actually operate in reality would be Yugoslavia. Our infrastructure is balkanized. Water people do not necessarily talk to electric power people, who do not necessarily converse well with transportation people, who do not necessarily talk to telecommunications people, because they have different business formats. They have different cultures. Some of them are privately funded, some of them are publicly funded. And I find that overcoming the institutional constraints is one of the most important aspects of dealing with hazards and dealing with infrastructure in an effective way. So let's tell some stories to see how some communities over many years have been able to deal with some of their hazards. And we'll start with San Francisco, which is sort of a very emblematic city in the United States. People often think of San Francisco as being one of the nicer cities in the world. San Francisco is about 120 square kilometers. And many people think of San Francisco as being composed of earthquake-resistant structures put together by modern engineering and codes and so forth. But if you look at the bottom picture there, if you look at this picture of these houses, 96% of the buildings in San Francisco are timber-framed structures. And San Francisco has a very high wind forces. It's very unusual to go to San Francisco and not have a windy day. And wind and timber and the potential for igniting a fire is one of the greatest threats in San Francisco. So fire following earthquakes is the defining hazard within the earthquake hazards for San Francisco. In fact, San Francisco burned to the ground in 1906, destroying 490 blocks of the city, partially destroying 90% of 32 additional blocks. It is still the greatest single fire loss in United States history. So what caused this? It was the ground. What you see on this picture is a map that was put together by the U.S. Geological Survey in a classic 1977 study by Lesyaud and Sinahuz called Historical Earthquakes in Northern California. And they went back and historically identified locations of San Francisco where the ground became unstable in addition to the shaking, and actually liquefied because of soil liquefaction hazards, which of course affect Mexico with your earthquake hazard also. This is a modern rendition of this map where all that information has been transferred into modern geographical information systems. And if we look at the water supply affecting San Francisco in 1906, 92% of it was supplied by the Lake Honda, College Hill, and University Mound reservoirs. And what I've done on this map is to superimpose the fire on top of the map with the liquefaction areas of hazard, and you'll see that liquefaction in Mission Creek cut off the entire water supply from the College Hill Reservoir to the University Mound Reservoir. Now at Cornell, we actually went out and found the oldest maps of the water supply from about 1912, did a hydraulic network analysis to understand what the situation was in 1906. And what you see on the right is the reservoirs that lost water in the simulation, which is the yellow, relative to the actual observations that were made by Hermann Schussler, who was the chief engineer of the water supply at the time of the earthquake. So you can see that the failure of the ground damaged underground pipelines that carried water, and that lack of water led to the inability to fight the fire, which eventually turned into a firestorm. This, in fact, is a picture of those 490 some odd blocks and some of the scenes of devastation which followed the earthquake. After that earthquake, the citizens of San Francisco decided to build a auxiliary water supply system, an independent water supply, high pressure, totally independent of the potable water supply system, the one that provides drinking water, which also is used for fire protection. But this became the backbone of fire protection. The initial stages, about 150 kilometers, were finished in 1913, and then over the years, it grew to about 250 kilometers at around the time of the 1989 Loma Prieta earthquake. As part of the design, they compartmentalized the system so that damage in these yellow areas that you see on the right of this map would not, where they expected liquefaction to occur, cause the system to shut down. They built the system and they waited 83 years until October 17th, 1989, when the Loma Prieta earthquake occurred. Much like this recent 7.1 magnitude earthquake, it was about 120 kilometers or so to the south of San Francisco, and ground amplification, site response elevated the acceleration and velocity levels there, causing liquefaction in liquefaction areas and causing some of the more serious destruction that was experienced at the time. Loss of water right here in this lower, this south of market zone of liquefaction actually shut off water to the entire central business district of San Francisco at the time. So when the fire, which you see on the right, erupted in the marina, there were no pipelines that could carry water to fight that fire. Fortunately, there had been simulations that had been developed, and again, Cornell played a role in these things, along with another company called EQE at the time, and Dr. Charles Scarthorne was the person who modeled the fire modeling. And those simulations were run, and they convinced Dianne Feinstein at the time, who was the mayor of San Francisco in 1986, to go for a bond issue. That bond issue was passed with 89% of the vote of the voters, and the auxiliary water supply system was enhanced. As part of that enhancement, they built a portable water supply system that could draft water from San Francisco Bay. So I'm going to move forward and show you what the portable water supply system looked like. Here's the portable water supply. There were 3 special fire trucks that carried 1.5 kilometers of 125 millimeter diameter hose, above ground pipelines and above ground hydrants, which then could be connected with the infinite source of water in San Francisco Bay and used to protect the central business district about 1.5 kilometers inward from the bay at various locations around the bay. And when the fire broke out in the marina, which I'm now showing in this illustration here, we were fortunate in the sense that because San Francisco is so subject to fire, there was not a breeze blowing that night. The fire in the marina looks like a candle, and that helped in preventing the fire from spreading. These hose tenders showed up. They were actually commissioned and made possible not by our simulations at Cornell, but by the vision of the person in this picture here. His name is Frank Blackburn, and Frank was the deputy fire chief at the time of the earthquake. He had personally undertaken to use the money that was passed by the voters in 1986 to put in a portable water supply system using those hose tenders. This is a picture of where the fire occurred in the marina. On the left, you see where the fireboat Phoenix came into the San Francisco Yacht Club, and 3 of those hose tenders came to that location, were able to relay water down to where the fire was occurring. So that's illustrated over here in the right, getting the water down to where the fire was, and they managed to extinguish the fire before it actually jumped Divisadero Street there and burned into the rabbit warren of sinuous and twisting roads that there was no natural fire break in the marina itself. In fact, Deputy Chief Blackburn said that without this protection, that they would have had to set up over here on Fillmore Street, which was the next natural fire break, because fire companies never let the fire get behind them, and therefore they would have lost this entire amount of the marina, obviously contributing to a great catastrophe. We actually had experience with the same type of situation several years after 1989 during the World Trade Center disaster. When the World Trade Center complex collapsed, it started to burn. And when it collapsed, it actually broke up all of those pipelines that went into those 40,000 person villages in the sky, and both 110-story tower structures fed water to 40,000 people each, and they contained very large diameter pipelines, which when they collapsed actually made a great draw on the water at the site. So they actually had to take the fireboats. So they took the fireboats that were commissioned in the New York City Fire Department, and actually they were able to supply something like 500 liters per second, which was able to augment only 300 liters per second, which came from what was remaining of the water supply because of the loss of pressure and flow, actually had reduced its pressures very seriously. Both of these events actually led to an improvement in the way people operate and line up to work with fires in various cities. And then there was a period of time where you would have thought that having made all of these adjustments for water supply in San Francisco, that there would have been additional hose tenders built, additional components to the portable water supply system. Actually, it was during that period of time, from about 1989 to about 2010, that the San Francisco Fire Department became underfunded, didn't have enough funds to support various firehouses, began to take them out of commission, had a civil action suit filed against them for not hiring minorities, and really didn't engage as much in their fire protection system. During that period of time, however, there was a bond issue passed by the voters of San Francisco for $4.5 billion in a water system improvement program that was built over a period of 10 years, from about 2002 to about 2012, 2014, that was predicated on setting standards for the performance of the system and really improve the water infrastructure in San Francisco in a tremendous way. During that period of time, the San Francisco Public Utility Commission became much more proficient at understanding how to operate their water supply system and to make things work better. And they eventually took over the auxiliary water supply system in about 2009 from the fire department. They both worked closely together and became the organization running that. I firmly believe that if the San Francisco Public Utility Commission of 2002, without that experience of building the water system improvement program, had taken over the auxiliary water supply system, it would have been very difficult for them to do that in a meaningful way. But having gained through time that capability, they were able to do that, and they were able to harness the force of the city and the politics of the area to pass an earthquake safety and emergency response bond in 2010 followed by another in 2014, which collectively provided $800 million to improve the infrastructure for the water supply in San Francisco through enhancements in the auxiliary water supply system and other associated structures. As part of that program, there was an augmentation of that early hydraulic network analysis to actually include 30,000 simulations of different fire scenarios and provisions of water to act as the backbone for planning what would be the hierarchy of infrastructure projects that would go in to improving the water supply in San Francisco. This improvement was based on information for performance criteria from the fire department. The city of San Francisco is divided into 37 different fire response areas, each of which is centered on one of the fire stations. And so that became the process for simulation, where the deterministic demands in terms of fire spread for a 7.8 magnitude earthquake was used to generate a probabilistic forecast of fire demands, and then a hydraulic network model that could account for instabilities in the hydraulic network because of all sorts of damage that would occur because of liquefaction was used to determine what was the probability of actually getting water there to meet the fire demand expected from this deterministic earthquake. And what you see was the first pass that was done with the existing water supply system. So you can see where the current auxiliary water supply system is. There was a good green area here, about 80% probability of being able to meet the actual fire demands. A terrible condition up here in the North Shore and other locations. So the engineers actually went to the San Francisco Board of Supervisors and came up with a hierarchical program for improving the water supply that actually turned all this area up here where the financial district is and all of the business activities that make San Francisco economically viable into green areas. And you know what the Board of Supervisors said to us? They said, nothing doing. Fire is not a problem only for the rich. Fire is a problem for everybody. You need to protect the entire community. Go back and turn that entire map to green. I was never more embarrassed in my life. So, social justice is part of our infrastructure because social justice is part of our communities. And communities and infrastructure are, as I said before, co-joined. They are one. We did go back. We did create a hierarchy of projects that will need to be built over the next 10 to 20 years. But with the 2014 bond issue already passed, there are projects underway to change and improve the conditions in San Francisco. Now, I came with a very flexible talk, and I knew that I was going to run out of time, and I think I'm just about out of time right now. So we'll catch you up in terms of, but I'll stop here. I actually have a part of this about Los Angeles also, and I would like to indicate to you, if I could, that there is a program in Los Angeles. And let me just, can I go ahead quickly on some of the slides? Excuse me. I'm going to go through some of these slides rather quickly because I really want to concentrate on one really important set of slides here. That is Los Angeles resilience. Los Angeles has a mayor. The mayor's name is Eric Garcetti. I look at Eric Garcetti as the replacement for Michael Bloomberg. Michael Bloomberg in New York City was the great infrastructure leader and mayor of our country. It takes leadership to build infrastructure. It takes leadership to build hazard-resilient infrastructure. And Bloomberg did a fabulous job in New York City. He, of course, served 3 terms, 1 extra term, by extraordinary vote of the city council to allow him to break a restraint on being able to run more than 2 times in a row. He then retired. Now the infrastructure leadership position in the United States has gone to Los Angeles because Garcetti is a superb leader. And he has put together, with the help of a number of geoscientists and engineers, a Los Angeles resilience plan that strengthens buildings, particularly soft story, non-ductile concrete, and we all know how problematic those types of structures are because that's shared in both countries, to fortify the water system for fire protection, resilient water pipelines, and to enhance telecommunications. And you can go to the website and you can type in Los Angeles resilience or resilience by design and see what the plan of Los Angeles is. One of the issues that needs to be treated in Los Angeles, and in fact all of Southern California, is the fact that the San Andreas Fault cuts off every amount of external water supply that enters into Southern California. And 85% of the water that provides water for a population of 22 million people. By the way, many economists say that just Southern California is the 11th largest economy in the world. A 7.8 to 8 magnitude earthquake on the San Andreas Fault can cut off the California aqueduct, the huge aqueduct that carries water from northern to southern California, the Los Angeles aqueducts, which are operated by the Los Angeles Department of Water and Power, and the Colorado River Aqueduct, which is operated by the Metropolitan Water District. 15% groundwater isn't going to do it, and even the reservoir supplies that MWD and LADWP have created in those systems is not going to do it either. This is America's Fukushima. If there was an earthquake that would cause a fault rupture here, the best of our abilities to predict the impact of that earthquake would be that it would take between 12 and 18 months to restore the water to the 11th largest economy in the world. That would really have an impact on the United States and, unfortunately, on most other people because of our close ties and strong economic bonds that hold us together. So, how do you solve this problem? You have the California Aqueduct, operated by the California Department of Water Resources, the Los Angeles Aqueducts, operated by the Los Angeles Department of Water and Power, and the Colorado Aqueduct, operated by the Metropolitan Water District. These are 3 regional entities. Now think about it. There's 6 permutations for their getting together and agreeing on things, and only one of them works. They all have to agree to solve the problem together. So that means we have, just to start with, about a 16% chance of getting this to work. And then I guarantee you there are institutional restrictions and constraints that further depreciate the possibility of these people working together. You would, and this is just water. If we brought electricity into this or transportation, it gets all that much more difficult. That's why I say that the institutional constraints are probably our most important. We have the technology, and more importantly, lately, we have the communities that want this done. We have the political will that's beginning to arise and actually require these people to get together. And they did. Historically, these 3 agencies met about 18 months ago and formed a united front and constant meetings with constant engineering and updates to improve and tackle this issue of the water crossing the San Andreas Fault. One of the areas is the Los Angeles Department of Water and Power. And what you see over here on the left is the Los Angeles aqueducts. They both go through a single tunnel, this Elizabeth Tunnel. Some people call it the Lake Elizabeth Tunnel. Some people call it Elizabeth Tunnel. It's only about 3 meters wide, and during the Great Shakeout, which was a simulation of an earthquake that occurred in 2008 with about 5.4 million people participating in this emergency response drill, the actual physical model for the rupture of the San Andreas Fault at this location was about 3.3 meters. Totally cuts off the water supply. what is being done, of course, is undertaking, and this is an expensive proposition, how to build a bypass tunnel. But in the interim, in the meantime, you can actually improve the ability of this tunnel to supply water for lesser magnitude earthquakes. So if we will close this tunnel at 3.3 meters at a 7.8 or an 8 magnitude earthquake, we also may sustain a 7 magnitude earthquake, which is only going to get it to move maybe 2 meters or 2.5. And there are ways in which people have prognosticated what this movement is related to the hazard and the probability of this hazard. So at that point, you're going to get collapse in the tunnel. How can you get some water through it? We're now using high-density polyethylene pipes. We've known from testing, we know that these are the most highly ductile types of pipelines that exist. And furthermore, you can hook them to pumps so that they can pump even more water through. And the current design concepts, and this is moving into design, is to put 1 or 2 of these pipelines in the tunnel so that if there's collapse, if there's fault rupture that doesn't go more than about 3 meters, because it doesn't occur at a single plane, it occurs over some distance, even in rock. You can still get water through these, and furthermore, there'll be a construction of steel, what we call sets, steel supports that will actually get the tunnel to perform ductily, as well as the pipeline protecting the water going through the pipeline system. So that is an example of resilience. And San Francisco is an example of resilience. And what do we learn? Well, in San Francisco's case and the Los Angeles case, we learned that infrastructure is a story. Moreover, it's a saga. It's a series of stories that are told and retold and lessons that are learned and relearned. And what we learn is it takes time. My own personal perspective is that dealing with infrastructure is like a football match, both soccer or American football, where it's all about field position and relationships. We wait for natural hazards to occur. And without the right field position and without the right relationships, we can't take advantage of the moment to be ready, and we can't take advantage of the moment to improve, because many times it takes a natural hazard and a disaster to stir us, to motivate us to do something. So the preparations in the interim are everything. Also, dealing with the institutional constraints. And I do believe, we see it in San Francisco, we see it in Los Angeles, that the political will is changing. People expect an infrastructure system that works, and they deserve it. Thanks very much.